group okay, is a set G with a binary operation which we will typically denote with a dot, but sometimes when we are discussing addition, we will write plus. So some notation that is convenient and meaningful in that context. Okay. So we will such that one, this is associative. That is A, B, C is A, B, C for all A, B, C inside G. 2, there exists an element E inside G such that EG equals GA equals E, GE equals E for all G inside G, and 3, for all G, there exists H such that GH is equal to HG equals E. Okay. So you will do an exercise in this thing which says that this element H in 3 is unique. Okay. So this is called the identity element. And again, the identity element will be unique, which will follow from bit of today's lecture and some exercises. And unique, I mean, given a G, the H is unique, okay, and it's called the inverse of G. Okay, so this is just a recap of the definitions, and we also saw various examples last time. So there is an important property of this operations that we have just defined, okay? That it is what is called cancellative property. This means for all G1, G2 inside G, and for all H inside G, okay, if G1H is G2H, then G1 is equal to G2. So this is A, B. If the other direction, other side, HG1 equals HG2, then G1 equals G2. So I'll prove one. The others consequences you should prove as exercise. I'll state them, but you should prove them as exercises. It is a way to get used to this line of reasoning. Okay. So proof of A. So G1H is G2H. Okay. There exists H1 inside G such that H1 is identity. Okay. So then multiply this. So therefore, G1H1 equals G2H1. But HH1 by associativity, so this we have done this way.
Hello, sir.
Yeah.
Sir, in either of the statement, if we just take H to be E, then we are done, right?
But the assertion is universal on H.
I mean, as it is true for all H, so we can. It is also true for H equal to E.
But we are proving. I mean, we are proving that this is true for all H. We do not know. I mean, I don't. Sorry,
Sir,
I
we
did not
know
understand
that it is true for all H, right? And then we prove
how do
that
we
G1
know?
equal to.
How do we know?
So I mean, if G1H is equal to G2H for all H, then G1 equal to G2, right? This is the statement.
Sorry. Okay, so okay, so sorry, it is a statement that, okay, so it's a okay, I understand your point. Now I understand. That is not, okay, so the way it is written, it is, I am not saying that if this is true for all H, then this is true. Okay, so it is probably the way it is written. Okay, if I just, suppose I write like this. I understand what the point that you're making is. Let me clarify what. Now,
Okay, sir. Now we
yes,
need to
yes, I
take a
am not
specific
saying that
case.
this G1H is equal to G2H for every H. I'm saying this implication holds for all H. The implication holds for all H, not the hypothesis holds for all H. Is that clear now?
Yes, sir. Yes, sir.
Yeah.
Now I understand.
So no. I mean, yes, See the, yeah. Okay. Uh, uh, yeah. So now, but using associativity, this is G1 times HH1. This is G2 times HH1. Okay? And this is just G1 times E. This is G2 times E. And this is G1. This is G2. Okay? And this proves A. B is an exercise. Okay? And a corollary of the statement that I want right now, which is that if Hg equals G, okay? So again, the quantification is for the implication, not for the hypothesis. Okay? So to make it precise, let me write it like this: that G and Hb inside G. Okay? If Hg equals G, then H is E. If GH is equal to G, then H is E. Okay, so this is yeah. So last time there was a question, okay, whether we can make subsets into a group or something like that. I forget the precise question. Okay. So I don't know. So I just wanted to make a remark. So I hope this. So proof is exercise. Okay. So because of this multiplication, associativity of multiplication, the existence of inverse, multiplication can be cancelled. Okay, so that's what the previous thing. Proof is an exercise. Okay. Okay, maybe so. There was some remark about something, whether some subset is a group or subgroup or subset is a group or something. I forgot the precise question, but in that context, let's look. So this. Okay, so let's look at it. Let's look at this following example. Consider Z, okay, with multiplication, not addition. Okay, this is not a group. Okay? Since there exists some n in Z, namely 0, such that for all m in Z, n times m is not 1, which is the identity of multiplication. Identity with respect to multiplication. Okay. There is 0 does not have an inverse, and that will show up in the cancellation thing. Okay. Therefore, we cannot cancel multiplication by 0. Okay, that is 0 times 1 is 0, which is also equal to 0 times 2, but 1 is not equal to 2. Okay. So in order to be able to cancel we need the existence of inverses. Okay? And associativity, I mean, all those things are satisfied here. Okay? Existence of an inverse is necessary, and as it shows, sufficient. Okay. So just to become familiar with this thing, let us look at subgroups of Z. So recall that a subset H, I mean G, let G be a group. A subset H inside G is a subgroup. Okay? If the identity element is inside H, first of all, H is closed under the binary operation for all. H is closed under the binary operation of G. Okay? That is for all H prime inside H, H dot H prime, where this dot is inside G, is inside H itself. That's a closed thing. E is inside H, and for all H inside H, H inverse is also inside H. This is the inverse inside G. Okay. So this is okay. So this is what a subgroup. This is what we mean by a subgroup. Okay. So let us write down what subgroups of Z are. Okay. So Z, in some sense, is the most primitive example of a group. I mean, there are smaller groups, but in some sense, it is easiest to start thinking about Z. So proposition. Let H be a subgroup of Z. Okay, so whenever we write Z, we mean Z plus. The operation is all plus. Then H is either 0. Okay, maybe let me state it, and then H is 0, or so I need to explain some notation, some things in context. So Z times A, where A is the least absolute value of any element in H. Okay. So if H is not 0, I mean, when again, this is either H contains only the element 0. Yeah, I'm so, okay, sorry. If subset is a subgroup is closed, and yeah. So we do say that the identity of element is inside H. So H is by definition a subgroup is non-empty. Okay? It contains identity element. Okay, so that's the least it can contain. I mean, that's okay, it needs to contain. Okay? So just a remark here before we. Okay. This thing. Okay, I mean, in any group G, okay, this and G are subgroups. The whole group itself is a subgroup, that because that satisfies this definition anyway. Okay? And the thing that I'll just speak. Okay, the subset, the singleton subset containing just the identity element, that is also a subgroup because again it satisfies all these conditions. So every subgroup therefore will contain this singleton set containing the identity element, and every and the whole. So that's the context of, I mean, just to explain. So a subgroup of Z will necessarily contain 0, okay, and the singleton set containing 0 is a subgroup. Okay. Otherwise, it is generated by some positive. It is so. What is this notation? So maybe I should just ask. Add another remark. Okay. By Z times A, we mean n times A, n is inside Z. Okay. So then, I mean, so every subgroup of Z looks like the singletons set 0 or all multiples of a fixed integer A, and that integer A is determined uniquely by this relation. Okay, so this is okay. So I hope the statement is clear. It is all integer multiples of the A, where A is uniquely determined to be the positive integer of least, to be the least absolute value of any element inside H. Okay, so proof. Okay. So if H is 0, there's nothing to prove. So assume that H is not 0. Okay. So it must contain some non-zero element. Okay. So let B be inside H, but not 0. Okay. Therefore, it will contain some positive element. Okay. Therefore, minus B is also inside H. Okay. Therefore, okay, okay. So in other words, H contains positive integers. So let's go back and look at this thing. It says minimum of the absolute value of an element of H. I'm sorry, of a non-zero element of H. Of course, the minimum absolute value of an element of H is 0. That's not what we want. Okay. Okay. So what is this minimum of an absolute value? Given any B, both B and minus B are there in H. Therefore, absolute value of B is also an element of H. Therefore, A, so note that minimum of absolute values of H, but not 0, is also the minimum of B, such that B is inside H and B is positive. I hope you can check this. Okay, any B that is positive and is inside H, of course, it is its own absolute value. Okay, so therefore the left hand side is less than or equal to the right hand side. Conversely, you take the absolute minimum of the absolute values. Okay? Since B belongs to H, minus B also must belong to H, and absolute value of B is either B or minus B. So absolute value of B also belongs to H. So therefore, left hand side is bigger than or equal to right hand side. So therefore, these are equal. So please check that this is, these two minimum are the same. Okay. So what we need to show, therefore, is that H is Z times A, where A is the minimum of B such that B is inside H and B is positive. Okay, so this is okay, so this is what we need to show. Okay, so okay, so A, note that A is inside H. Note that A is inside H by whatever we just discussed. Okay, because well, okay, A is a minimum of some numbers which are also already inside H, and therefore A is also by definition inside H. So therefore, H contains the group all multiples of A. Because any multiple, I mean, yeah, so maybe I should have clarified. I mean, I should have at least stated this. N times A, so there is no multiplication. The operation is addition. Okay, so is an abbreviation for A plus A plus A n times, okay, or, I mean, this is if n is positive. If n is non-negative, or for minus of that quantity, minus n times if n is negative. Okay, sorry, I should have said this earlier. It is the way I've written it is confusing because there is no. I said that the operation is addition, but then I'm just suddenly saying n times A, and it is confusing because both n and A are integers, and I'm pretending as if there is, or I'm incorrectly giving you an impression that there is some multiplication. That is not true. When I write n times A, or when we all write n times A in the context of the additive group Z, we mean this. Okay? If n is non-negative, we add it that many times. If n is negative, we add it, we take the additive inverse of A added to itself minus n times. Okay, so this is, I should have said this when I said, what do we mean by, okay, I mean, I should have said that here. Okay, let me put a see note in red on the next page. Sorry, I should have. Okay, so Z contains A, therefore it will contain A plus A, A plus A plus A, and also the additive inverses of these things. This is what we mean by n times Z, okay, for as n runs with all values of Z. So H contains this one. So what we need to show is, okay, so we need to now show, right, to show that H is a subset of ZA. Okay, that's what we need to prove equality. So we have proved one containment, we need to prove the other. Okay, let B be inside A, B be inside H. Then we use this Euclidean division that we know. Okay. Then there exists a Q and an R inside Z such that B is Q times A plus R. So this is just division with remainder. Okay, that's all that we're doing. Okay, and what is the property of R that characterizes this? R is positive, and R is non-negative and strictly less than A. So given any integer B and a positive integer A, we can always get like this. Okay, so this is what we have. Now let us look at what again. Okay, so now B is inside H. By Q times A is just A plus A plus A. So it's one of these things. If Q is non-negative, the same argument, and minus of A plus up to A minus Q times if Q is negative. Okay, Q times A is this one. This is also B. Sorry, let me write a proper sentence. Now B is inside H. Okay. Since Q times A is this, Q times A is also inside H. Okay. Therefore, R, which is B minus Q times A, which is B plus negative of Q times A. So I'm just writing it pedantically so that I'm only using the operations in the negative here means additive inverse. Okay. There's no subtraction. Okay. Subtraction is adding the additive inverse. Okay. So just for now, I'm just writing it pedantically, but sooner or later I will stop doing it. Okay. So B is inside H and QA is inside H. Therefore, minus QA is inside H. Therefore, the sum is inside H. Okay. So R is a non-negative integer, okay, strictly less than A. That's also inside H. So this implies that R is in R0. Okay, since by definition of H, by definition of A is the smallest positive integer that is inside H. Okay? So if R is strictly positive, then it will give us a contradiction. So that can't happen. Therefore, R must be 0. That is, B is Q times A. So B is also inside Z times A. Okay? So that is okay. I mean, the mathematics behind this proof is not new to you, but the way it is expressed or the way it is written, it may be new to you. And this is the sort of argument that we will again see, if not now, but if not in this semester, but when you do ring theory, etc. Okay? So it would be worthwhile to just go over it. Okay? Even though the mathematics that we have used in writing out the proof is something that we all knew from even before we got to high school. Okay? But thinking of it as a group and sort of making sure, checking that this agrees with the definition in those sort of things should become familiar. Okay, so that's the end of the proof. Okay. So every subgroup, yeah.
Sir, can Q really be negative? I mean, in the
well, that depends on what B is. There's no need to assume that B is positive.
Okay.
Yeah, I mean, it doesn't simplify the proof anyway.
Yes.
As opposed to the proof does use that A is positive, right? But
yes,
not
yes.
that B. We don't really care. It's about B. Yeah. Okay. So another another useful remark. Let D and E be integers, okay? And let us say that E is non-zero. Then we can talk about, you can ask whether E divides D or not. Then E divides D. What does this mean? I mean, when you say divides, okay, here, what does that mean? It means that there exists an n in Z such that D is n times E. Okay. That's just by definition. That's exactly it. But what does this mean? This implies that D is in the ideal generated by E. I'm sorry. D is in the subgroup generated by E. I should not have used the word ring theory 2 minutes ago. I just generated by E. And yeah, so what does this mean? So this means that every multiple is also a multiple of, some 5 times D would be whatever 5 times whatever times E. This is what. Now let us look at the last statement. ZD is so this is a subgroup. Maybe I should not just. ZD is a subgroup of ZE. Okay. Let us look at the last statement. ZD is a subgroup of ZE. So in particular, it is a subset. Okay. Therefore, ZD is a subset of ZE. Therefore, D is an element of E. So that's the last statement implies the last but one statement. Okay. And D is in Z times E is precisely the statement that there exists. So this is an equivalence. So E divides D precisely when ZD is a subgroup of ZE. both of which are themselves subgroups of Z. It's a useful remark. Again, as I said, most of the group theory statements that we prove about Z, the mathematics behind them we knew before middle school, okay, primary school, maybe definitely before we came to high school. Okay? But it is just the way that we want to formulate it in the sort of language, in this language, which we will then be able to use it in other contexts. It's just one remark. Okay. So we talked about subgroups. Okay. So now definition. Sorry, it's I want to make some assertions and then make a definition. Okay. So let G be a group and a subset of G. Then we can ask, and this is, okay, we often come across similar questions in various contexts. Okay. We look at subgroups of, so what is this thing? So we're going to take a intersection over some H. H is a subgroup of G and A is inside H. Okay. So when we are intersecting all subgroups of G that contain A. So this thing. Okay. So then, so I just want to call it maybe G sub 0 because I need to use then. G0 is a subgroup of H, subgroup of G. A is inside G0, and if G prime is any subgroup of G containing A, then A is inside G prime. So in other words, it is the smallest subgroup, that is G0 is the smallest subgroup of G containing A. Okay, and now we can define, okay, we say that G0 is the subgroup generated by A. Sorry. One more sentence before I. Sorry, I needed to have said one more thing before I said this. Okay. For every G in G, G in G0, we can write G0 as G as A1 up to some AK for some K and some integer K, and A1 through AK inside A. So I'm writing this as product. I mean, the group operation is thought of as product, just notation. So therefore, we say that G0 is a subgroup generated by A. Okay. So this part I leave as an exercise to you to check. These are not very difficult. Okay, but it will get you used to thinking about along these lines. Okay. Okay, but the first part, I hope it is sort of clear from definition. Okay. G0 we are taking as the intersection of all subgroups containing A. Okay. So therefore, if some G and G prime, so identity element in every H is in every H, so it is also in G0. For every element in G0, its inverse is in every H, therefore the inverse is inside G0, just by properties of intersection. Okay, and of course it is closed under. So okay, so this also you need to check. Okay, so I am doing it. I mean, if you have difficulty, you can talk to the TAs, but I want you to try. Okay, these are not at all difficult proofs. Sometimes it is just getting used to this formal argument, and this is the best time to get used to it. Okay? So you should do these things.
So in the last statement, you asked us to check only holds if A is closed under inverse, right?
This is what? No. H is the one that needs to be closed under inverse.
No, but
sorry. Okay. Oh, this one. Yeah, correct.
Yeah.
We can write. Sorry, I forgot the exponents. So correct. No, sorry. Thank you for. Yeah, this is. So I don't want to call them A1 through. So I will call them B1 through BK, and for some K integer K, and sorry, we can write. Okay, where K is an integer, and for all 1 I less than or equal to K, Bi is inside A, or Bi inverse is inside A. Yeah, I incorrectly stated it the way that A will also contain elements of inverses of its own elements. That is not at all guaranteed, and it's not even required. What you need is, when you take the products of these elements, you should consider not just elements of A, but also their inverses. Okay? I mean, the such sequences B1 through BK, when you take the product, okay, I mean, each Bi can either be an element of A or the inverse of an element of A. Okay, so that is the okay. So this is, so please check things in this remark. Okay, so that's what we mean by saying subgroup generated by A.
Sir?
Yeah.
So could you scroll up for a...
Yeah, sorry. Is this fine?
Yeah, sir, here you've written... No, a little more, sir, could you...
Little more up, yeah.
Yeah, here you've written
Yeah.
if G dash is any subgroup of G containing A, then
Yeah.
A is contained in G dash.
Yeah.
Uh,
Correct.
so, I mean...
I'm sorry. I'm sorry. Correct. That is not what we needed. G0 is contained inside G. Thank you. Correct. I mean, the other statement is also true, but it's not clear how it helps.
Yes.
Yes. Yeah. G0. I mean, G0 is the smallest subgroup generated containing A. Okay. And we because of the next property, we will also refer to G0 as a subgroup generated by A.
Yes.
Okay. Okay. So now, let's so that these ideas become more. Let us go back to Z. Okay, so back to Z. Okay. So let A be a subset of Z. What is the subgroup generated by A? Okay. So of course we know what subgroups of Z are. It's either the trivial group just containing 0, or it is a multiple of some positive integer, all multiples of some positive integer. Okay. So it is going to be one of this kind. So if A is empty, so if A is empty, then so let us say, what is a subgroup G generated by then G of Z, then G is just the intersection of all subgroups containing the empty set is the trivial subgroup. If I mean, and this is also true if A is just the singleton set 0. if A is a singleton set A, then G is ZA. Okay. Of course, it must contain all multiples of A, and it need not contain anything further because anything further will have more elements. So it is a multiple. Okay. So now let's do this. So it's proposition. Right. So I'm just going to address what happens when A has two elements. Okay. So let A, so another piece of notation. When we write, not when we write ZA plus ZB for the set, for the subset, n times A plus m times B, and then m integers. Okay. So this is the remark. Okay. This is the subgroup of Z generated by the set AB. This is, I mean, of course, it is a subgroup, and this is the smallest subgroup containing A and B. Okay. So this is just okay. So now let us prove as a proposition. Okay. Let A and B be inside Z, and at least one of them is non-zero. So at least one of them is non-zero. Okay. So of course, so if you look at ZA plus ZB, it must be generated by one element. Let's call that thing D. Let D in Z be the element, such that ZA plus ZB, so the smallest subgroup containing A and B, is ZD. So such a thing exists because every subgroup of AB, every subgroup of Z looks like Z times some D. Okay, so let this be then. What is this D? It's a number that we know. D is the GCD of A and B. That is, sorry, I want to take a positive integer here. That is, just to get some uniqueness. Otherwise, it is difficult to say D GCD. That is, D divides A and D divides B, and for all common divisors, this is the largest. For all E in Z such that E divides A and E divides B, E also divides B. Okay, so this is the largest common divisor. The E here are the common divisors, and D is the largest because every E, so it is a GCD. And two, there exist some R and S inside Z such that D equals RS plus RA plus S times B. Okay. So the GCD can be written like this. That's the proof. So I hope the statement is clear. We take two integers, A and B, at least one of them is non-zero. Then we are looking at what is the subgroup generated by A and B. First of all, it's going to be some Z times D. So that, okay. And then that D is the GCD, and D can be written as a Z linear combination of A and B. That's what's saying. Okay. So proof of 1. So earlier, just look, that's why I wrote this remark here. An integer divides D if and only if ZD is a subgroup of ZE. So here, D divides A. So that's not, okay. No, that's not what we said. We said that ZA plus ZB is inside. So A is inside ZA, which is a subset of ZA plus ZB, which is equal to ZD. Therefore, D divides A by the earlier remark. Okay. Similarly, D divides B. So D is a common divisor. So we just now need to check that it is the GCD. Yeah. Yeah. So now suppose E divides A and E divides B. This means that A is inside ZA, ZE, and B is inside ZE, which means that ZA plus ZB is contained inside ZE. That is, ZD is inside ZE. This means that E divides D, again by the earlier remark. So this containment of subgroups inside Z, okay, is equivalent to divisibility. Okay? So this is what we are using. Okay? That's what the earlier remark said, and that's why we just keep using. Okay? So therefore, D is the GCD of A. Okay? So now to prove 2, ZD is ZA plus ZB, which means that D is inside ZA plus ZB, which means precisely that there exist R and S inside Z, such that D is of the form RA plus S. Okay? That is, the GCD can be written as a Z linear combination of the elements. Okay. So another proposition, which I will not prove, just since we discussed GCD, let us also discuss LCM. So let A, B be inside Z be non-zero integers, both of them non-zero. I suppose it's not really. Yeah, I don't know how LCM is defined for zero, non-zero integers. Okay. Then ZA intersect ZB. This we have used earlier. If you intersect two subgroups, we get a subgroup. Okay. That is what, in the definition of the subgroup generated by, we use that implicitly. I mean, we used it. So I'm just, okay. This is Z times the LCM of A. Okay. So of course, Z times the LCM is inside Z times A and it's inside Z times B. So that proves one containment. And for the other containment, you should. Okay. So proof is left as. Sorry, I'm leaving these as exercises because I want you to think about these things. These are not difficult. Okay. The mathematics is easy. It is just that I want you to become familiar with formalizing it like this. Okay. So that is about things about Z. Okay. So I want to talk about two more topics, just briefly, important things that are in this context. Okay. What is called group homomorphisms. So this is the definition. let G and H be groups. Okay, so they have some underlying binary operation which I am not denoting. It is understood that there is something, unless there is some requirement. So then I will write it. Okay. Group homomorphism phi from G of phi from G to H is a function such that phi of G prime is phi of G prime for all G and G prime inside G. Okay, that is, it respects the multiplication, I mean the group operation. Okay, so just to clarify, this is the group operation in G, and here is the group operation in H. Okay, although we are denoting it the same way, just keep in mind that the actual operation is being done in two different sets. Okay, so then we know some examples already. So let me discuss these examples before getting to the property. Okay. So if you take Z mapping to Z, fix an integer. Okay. Then F from Z to Z, an arbitrary integer goes from A, okay, is a group homomorphism. Okay. That is, F of n plus m is F of n plus F of n. Okay, so here it's addition, so we write it. Okay. So when I say group homomorphism, the group is both are Z. Okay. There are less, I mean, more slightly more complicated examples. Okay. The determinant function from GLN R to this is n by n matrices, invertible matrices over R to R. Okay, so these are the non-zero elements of R, and the group operation now is multiplication, is a group homomorphism. Yeah. That is, determinant of two matrices is determinant of A times determinant. So here is matrix multiplication, and here is multiplication inside R. So this is an example of a group homomorphism. Another example is Z with addition to any group. And A an element of G. Then the map from the addition Z plus to G, okay, in which an integer n goes to A times n. Okay, so A is some fixed thing, and we're making a statement. And what is this? What is this? Okay. A n times if n is non-negative, and A to A minus n times inverse otherwise. If n is negative. Okay, so this is a group homomorphism. And 3. So what are the things that we saw? Z goes to multiply fixed element, determinant, something inside an arbitrary group. So this is 4. The exponential map from R plus to this. Okay, some t goes to exponential of t is a group. I mean, it is sort of related to the previous one. Okay, this is example. Another example is the absolute value map from non-zero complex numbers to non-zero real numbers. Some z goes to absolute value of z is a group homomorphism. So there are, so the group homomorphism come in very many, in quite a few contexts. And in most of these contexts, the maps, the function already existed. Okay? I mean, exponentiation map already existed. Absolute value map already existed. Okay? We knew about it. It is just that we're now learning that it is also group homomorphism. Okay, just a minute. Yes.
Sir, what are the operations in the last example?
Oh, sorry. Okay, I apologize. When we say R, this is always. Yeah, it is.
Okay.
I mean, it is always a non-zero elements under multiplication. Yeah. So in fact, Artin doesn't even put the dot there. For him, if he writes a field and puts a star on top, I mean, times symbol on top, he says it is now multiplication. He doesn't. But yeah. So it's a proposition. Let phi from G to H be a group homomorphism. Okay, so implicit in the statement is that G and H are groups, but if I without explicitly saying that, so for all A1 through AK inside G, phi of A1 through AK is phi of A1 times phi of AK. I mean, it is not, I mean, by definition, it was only for products of two elements, or the operation, it was just defined for the binary operation, two elements, but it can be the same property will also hold if we do it for more. Okay, I mean, remember, okay, I just when I prove phi of E. So here I will denote okay. So I'm writing this. This is the identity element of G. This is the identity element of H. That's why I put the subscript, just to make. Okay. I mean, we will not do this all the time, but just for now, for seeing it for the first time. Okay. For all G inside G. Yeah.
So it should just be EH in the
I'm
second
sorry.
step.
Yes, it's correct. EH. Okay. For all G in G, phi of G inverse is phi of G inverse. Okay. So not only does phi respect the group operation, it also respects the identity element and taking inverses. So proof of 1, okay, induct on K, and we note that A1 through AK is A1, A2. So I mean, it has to be written using associative AK -1. AK. Okay, so therefore, when you apply phi, you're applying phi of A1 times the phi of the product of A2 through AK, and then just by induct. Okay, so that's proof of 1. 2. So what is, okay, so phi of G is, so let G be inside G. So I'll put the quantifier in a minute. Phi of G. Okay. So G is same thing as E times G. Okay. So this is EG times G. Okay. That is, I'm just writing that G is EG times G. This is phi of EG times phi of G. Okay. So this product is inside G, and this is inside H. So phi G is phi of thing. So now use the cancellation. Multiply by the inverse of. Okay. So let H be the inverse of phi of G, okay, in H. So then phi of G times H is phi of EG times phi of G times H. But this is, so these two cancel. So this is identity of H, it's inverse. And the right hand side is, we just cancel phi G. Okay, I didn't need to write this out. We had already checked this earlier. We just cancel the phi G on both sides. This is what we wanted to show. And 3, what is 3? 3 was that it respects. Yeah. Okay. So EH is phi of EG. Yeah. So what is the quantifier for G? It doesn't really matter. It doesn't matter for all G. EH is EG, phi EG is what we just established. This I want to write as G inverse. Okay. This is inside G. Okay. This is phi G times phi G inverse. Okay. This is true for all G inside G. Therefore, phi G inverse is the inverse of phi G. Phi of G inverse is the inverse of phi G. Okay. The inverse here is inside G. This is inside H. Okay. The first time we are doing these things, let us write it in all this glory. After a while, we will just not even bother to mention. I mean, that's, we all will get used to. Okay, so this is the point. So not only does this this operation respect just the taking product of two elements, it respects products of any finite length because it's done by induction. So it's okay, finitely many elements. It respects taking inverses and it respects the identity element. So this is, and if you recall them, if you look through it, the proof does explicitly use that in groups you can do cancellation. Okay, so this is okay. So this is so one couple of definitions. Let phi from G to H be a group homomorphism. This is really not a definition. Let's call it proposition. Then, image of phi is a subgroup of H. Okay. So, image of phi, we know what it means. elements that can be written as phi of G for some G. Okay? The image as a function. So this is as a function, that is the set of all H inside H such that there exists G inside G such that H is phi of G. Okay, so this is a subgroup of H. The proof is proof. So I'm not, yeah, so this is called the image subgroup. Therefore, EH is phi of EG. This is inside image of phi. Okay. And it is, of course, closed. Okay. So for all H prime inside image of phi. Okay. So let G and G prime inside G be such that H is equal to phi of G. H prime is equal to phi of G prime. So therefore, H prime is phi of G prime. This is also inside image of. And so it is a subgroup. It is, and inverse is also. Okay. Phi of G inverse is phi of G inverse. That's also inside image of. Okay. Therefore, this is this ends the proof. Okay. So we will, the image of the function is also a subgroup. So we will often refer to it as the image subgroup. Okay. So this is one. Okay. A definition. The kernel of let phi be a group homomorphism. Okay. The kernel of phi is the set G inside G such that phi G is EH. This is from G to H. Okay. Proposition 1. Kernel of phi is a subgroup of G, and 2. Phi is injective if and only if kernel of phi is a singleton subgroup containing just proof. So I'm sorry, this is the same way it is proved for vector spaces. Okay. Kernel of a linear transformation is so linear transformations are examples of group homomorphisms. We remarked yesterday that vector spaces are groups under addition, vector addition, okay? And linear transformations are certain kinds of group homomorphisms. There could be other group homomorphisms. Okay? But linear transformations are group homomorphisms. So this is what so similar argument here also. I mean that kernel is a subgroup. Okay, so EG is in kernel of phi because phi of EG is EH. Okay, for all G prime inside kernel of phi, phi of G prime is EH. So it is closed under product. Okay. And phi of G inverse is phi of G inverse is EH inverse is EH. Okay. So G inverse is also inside kernel. Okay. So it is a subgroup of G. And 2, if phi is injective, okay, then kernel of phi, which by definition is phi inverse of EH, is a singleton set. since EG is also always inside kernel of phi, okay, kernel of phi is EG. So injectivity implies that for every element inside the image, the pre-image contains exactly one element. That's what injectivity means as a function. Right? So it's a singleton set, but it already contains one element, and therefore that must be all the elements. Okay, so the one, if it is injective, then we get this condition. Conversely, suppose that kernel of phi is a singleton set. Okay. So again, this is a proof similar to what one would argue for injective linear transformation. Okay. So let G. So we want to show that. So let G and G prime be inside G be such that phi of G equals phi of G prime. Okay. We want to show that these are equal. I mean, G equals G prime. That's what injectivity shows, right? So that's what we want to show. So this implies that phi of G inverse times G prime. So on the one hand, it is phi of G. Okay. So this is equal to EH. But we are assuming that kernel of phi is a singleton set. So this now implies that G inverse G prime is EG, which implies that G equals G prime, which is what we wanted to show. So that therefore phi is injective. Okay. You would have used a similar argument to show that a linear transformation is injective if and only if its kernel is trivial. So it's the same similar argument. Okay. So there was another topic called cyclic groups that I wanted to discuss, but I think it's already time, so I'll just stop here. Okay. So whatever up to this point, okay, this is what is included in the midterm. Okay. So I mean, I hope because this I mean we have just begun discussing groups. We are discussing relatively simpler things, okay, as opposed to the more complicated things that we were discussing about bilinear forms. Okay, so I hope it's okay in the midterm. Okay. Okay. Thank you.
Thank you, sir.